July 1976. Radio operators around the world, both amateur and professional, found themselves facing a bizarre anomaly. Without warning, their broadcasts were assaulted by a haunting sound, a sharp, repetitive tapping, often likened to an electronic woodpecker. Everyone from radio hobbyists to aviation control towers, plus even legitimate nationwide radio broadcasters, all heard the signal at 10 Hz. None were able to prevent it rudely interrupting their broadcast seemingly at random, and no explanations as to where the woodpecker was coming from were forthcoming via the US government or otherwise. Keep in mind that this was at a time when Cold War tensions were peaking and nerves were already frayed. So of course, it wasn't long before concerned speculation gave rise to an avalanche of conspiracy theories. What the radio hobbyists of the world, and specifically America, where the woodpecker was most commonly heard, didn't know is that they were hearing the over-the-horizon or OTH Duga-1 radar array, otherwise known as the Russian Woodpecker, or as NATO military intelligence referred to it, steel yard or steel work, a name derived from the fact that the Duga radar receivers were absolutely enormous structures, measuring 700 meters in length and 150 meters tall. That's 2,300 feet in length and 490 foot tall, which makes them amongst the most expansive ever built. More to the point, the radars were allegedly capable of outputting a staggering 10 megawatts, a very impressive number at the time. As a point of comparison, the cutting-edge Ames Type 80 radars used by the UK's Royal Air Force between the mid-50s and early 90s had an output of between 1 and 2.5 megawatts. The American AN/FPS-85, on the other hand, had a peak output of 30 megawatts, though this was intended to track objects in outer space. Power output doesn't necessarily translate to radar being accurate or reliable, though, as we will see a little bit later on. Of course, civilians at the time didn't know the signal was the Duga radar, and some insisted that the woodpecker signal was part of a Soviet brainwashing operation threatening to either turn Americans slowly Soviet or perhaps simply reduce anyone in earshot to a mindless zombie. Others pushed a conspiracy theory that actually still exists to this day, linking the mysterious radar signals to weather anomalies. The signal was, the theorists insisted, a byproduct of weather modification experiments that would ultimately destroy America through drought or devastating storms, which never happens. Russian woodpecker interference was an unintended side effect of the backscattering techniques used by the Duga radars and were an international problem until the end of the 80s. The interference was such a problem that radio broadcast equipment was eventually designed with a built-in dampener to counter the signal, referred to as the woodpecker blanker. But although the interference itself could be dealt with, the much more pressing issue was understanding if there was any real, credible threat to concerned American citizens. Thankfully, it didn't take long for motivated radio hobbyists and amateur investigators to collaborate with signal triangulation techniques, thus quickly confirming that the signal was indeed originating from the Ukraine near Chernobyl. The Duga radar receiver at this location is one of the most commonly mentioned and referenced in popular media today, though an often overlooked second Duga radar system also existed in eastern Siberia, built soon after the first. Of course, once 70s investigators confirmed that the woodpecker signal was coming from the Soviet Union, Americans weren't exactly comforted. The paranoia dial was now turned up to 11, and legitimate tinfoil hats were a hot fashion accessory around that time. Though in these circumstances, who can blame anyone for trying to protect their brain from an unidentified Soviet radio signal, lest they be turned into a zombie? However, while some chose tinfoil hats, others were more proactive. A group of radio hobbyists banded together and called themselves the Russian Woodpecker Hunting Club. They set about attempting to jam the radar by broadcasting a directly opposing signal of their own. The group would perhaps have told you that they were transmitting synchronized, unmodulated continuous wave signals on the same pulse as the woodpecker, but what this really came down to was tapping a ham radio microphone in synchronicity with the woodpecker. It may sound a little silly, but the hobbyist group was actually using a sound principle, and at least in theory, it may have been somewhat successful. Similar techniques were almost certainly used by the US military, though of course with powerful high-grade equipment. And on that note, we'll come back to how easily the Duga radars were jammed a little bit later. As the Russian Woodpecker Hunting Club was tapping microphones, other, more skilled investigators were unraveling mysteries and drawing conclusions. A binary phase shifting key, the same BPSK used in the local area networks of modern computers and in wireless Bluetooth devices, was identified in the woodpecker signal. Investigators likewise noted that the pulse exhibited clear signals of uninterpretable communication barcode codes. Thus, all but confirming that the signal was an over-the-horizon OTH radar system, one located in Ukraine and pointed towards the United States. OTH radar systems were a cutting-edge technology at that time, with the US, UK, Russia, and various other countries all actively developing their own versions. The political climate of the Cold War had above all else put countries into a mad scramble for the ability to identify rocket launches at extreme long range. Satellites would ultimately come to serve that purpose, but prior to that technological leap, OTH radar was the best solution for seeing incoming nuclear war before it happened, even if just by a few minutes. At the time Duga 1 went online, America already had an expansive early warning radar system of its own, including the 5-megawatt RCA-474L ballistics missile early warning system, or BMEWS, and the already mentioned 30-megawatt AN/FPS-85. The FPS-85 was widely publicized as being capable of tracking a basketball-sized object at 40,000 kilometers in outer space, and so the military partially hijacked the tracking capabilities to scan for ballistic missile launchers instead, specifically from submarines. In the spirit of the frequent military posturing that characterized the Cold War, Russia was quick to claim that the US's early warning detection system wasn't as impenetrable as it appeared. Soviet Premier Nikita Khrushchev in 1961 proclaimed, "You, the Americans, do not have 50 or 100 megaton bombs. We have bombs more powerful than 100 megatons. We placed cosmonauts in space, and we can replace them with other loads that can be directed to any place on Earth." Khrushchev was referring to the terrifying fractional orbital bombardment systems, FOBs, which effectively made all US early warning systems useless. Given the orbital trajectory of FOB missiles, a warhead could theoretically approach from any direction, skirting around radars and striking with little to no warning. Khrushchev declared that Russia had developed such a system, as he repeated in a speech during the Cuban Missile Crisis in 1962, saying, "We can launch nuclear missiles not only over the North Pole, but in the opposite direction too. Global rockets can fly from the oceans or other directions where warning facilities cannot be installed. Given global missiles, the warning system has lost its importance. Global missiles cannot be spotted in time to prepare any measures against them." Soviet Russia, meanwhile, was itself surrounded by threats on all sides, with the West having intercontinental ballistic missiles, ICBMs, in Turkey, Europe, Asia, and of course America. Whoever did or didn't have the upper hand is an endless topic of speculation, but either way, both countries had serious need for improved early warning systems given the frankly insane Cold War political situation. More to the point, the systems certainly had to be well beyond the World War II era line-of-sight LOS radar systems. World War II LOS systems had been strictly short-range, only good for aircraft detection up to a few hundred kilometers at their peak. This short-range detection had been extremely useful, doing wonders in providing military units with an essential but brief warning of approaching bombers. But as World War II came to an end and technology advanced, the biggest threats were obviously no longer incoming aircraft, but incoming long-range missiles. The infamous German V-2 rocket had demonstrated beyond a shadow of a doubt just how devastating long-range attacks could be, with a then revolutionary weapon capable of hitting targets at a distance of 320 kilometers. Thus, Russia, along with the US and many other countries, focused on radar systems that could detect a missile launch at thousands of kilometers, thereby providing enough time for a well-thought-out response. The goal was that with long-range radar detection, a window of between 12 and 15 minutes should be granted, depending on where the missile launch originated. A number of experimental OTH research projects took place during this era, including the Multiple Storage Integration and Correlation Project, or MUSIC, which was developed at the United States Naval Research Laboratory in 1955, and the Magnetic Drum Radar Equipment Project, MADRE, at Chesapeake Bay in 1961. But naturally, going from short-range to long-range detection was about far more than just upping the power of a radar and achieving longer-range detection. The problem was, simply put, that the Earth curves. Now, there is no detailed development history of the Duga radar system, with virtually all of the information lost forever behind the Soviet Iron Curtain. Much of the information that does exist, at least as far as the construction and operation of the radar goes, comes from Volodymyr Musiets, a former commander of the Duga 1 complex. But even the information he provides is vague at best, giving only a glimpse into how Duga was developed and deployed. Some very spotty information available beyond ex-commander Muziet alleges that a working OTH radar was built by the Soviets as early as 1949, referred to as VAR. Assumptions are that although the Soviets could see the potential of OTH with VAR, they also understood that further technological advancements were necessary for OTH to be practical. That's probably why there's no further information of Soviet OTH research and development until the 60s and 70s. A working experimental version of the Duga was then built at Mykolaiv in Ukraine during the early 1960s, with the system reportedly able to detect rocket launches 2,500 kilometers away. A follow-up, equally as successful prototype was built on the same location, again demonstrating the potential of OTH and prompting the full-scale construction of the famous Duga-1 receiver that is the structure that's still standing, with the separate transmitter having been located around 60 kilometers away at the military town of Lviv-1. The transmitter has since been entirely dismantled and removed, which is probably why that half of the Duga-1 radar is often overlooked. Only the Lubech-1 military town now remains, where the transmitter once stood. First off, to help put the technical Duga radar information into a sensible framework, let's understand the differences between low and high radio frequencies. Low frequencies, between 30 and 300 kHz, tend to travel great distances, are much less likely to suffer interference from weather, and can penetrate buildings and other structures with relative ease. On the other hand, low frequencies also have limited bandwidth, making the potential transfer of information modest at best. If you're making a voice call on your cell, this is on a low frequency. High frequencies, between 3 and 30 MHz, are what you'll find in a Wi-Fi router and on 5G towers. High frequencies have a much broader bandwidth and are therefore capable of transmitting dramatically more information very quickly. But high frequencies travel far shorter distance and are easily disrupted by physical structures or bad weather. These inherent limitations are why 5G towers require so many relays to be effective, given that the signal must be repeated constantly to provide reliable coverage. Another very important property of high frequencies, not seen in low frequencies, is that high frequency bounces off the Earth's ionosphere. So, how does that relate to the Duga radar? The system used broad bandwidth high frequencies, and given what we've just learned about the waves not traveling very far and being easily disrupted, you'll already start to understand just how challenging it must have been to get the radar working as intended. That's also probably why the radar had a higher than average output of up to 10 megawatts, assuming that the information about output is indeed accurate. Secondly, and more importantly, the Soviets needed to take advantage of the ionosphere bouncing properties of high frequencies. And this is a good time to mention that the word Duga translates to arc, referring to the route taken by the radar beam over the horizon. Now, radars use microwave beams, broadcasted in a focused straight line, with any waves being sent back, reflected off a solid object such as an aircraft, received as readable information. In the case of World War II LOS systems, the range of this beam could be extended in various ways, such as by elevating the radar to compensate for ground scattering. So, generally speaking, an elevated 200 kilowatt World War II LOS radar could detect an object above ground at a reasonable distance, assuming a clear line of sight, up to around 160 kilometers depending on circumstances. However, the key here is that no matter how much you increase output or elevate a radar, the beam is still limited to functioning in a straight, unbroken line. So at a certain point, your beam is simply going to be shooting off the planet and into space, not serving much purpose other than, likewise, sending your electricity bill into the stratosphere. Hence, if you want your radar to detect something, say, on the other side of the world, what you need to do is intentionally bounce your radar beam back down onto the surface of the Earth. The beam will then reflect along the same route it arrived on and be accepted and analyzed by a receiver. There are other workable solutions to OTH radar detection, such as using further traveling low-frequency waves and essentially scattering them along the ground to eventually refract around the surface of the Earth, but this solution, referred to as using ground waves, is less accurate than the alternative and works best when used over the ocean, where refraction is more reliable. The ground wave solution is therefore reliable for tracking ships, but less so if you intend on detecting missile launches. Skywave, or skip communication, refers to the use of the ionosphere, the charged layer in our atmosphere that exists between 48 and 965 kilometers above sea level, to bounce low-frequency signals back onto the surface of the Earth. This method has been used frequently throughout history, though primarily as a means to extend the reach of radio and TV broadcasts. The technique is, and still is today, fairly common, though much less so since the adoption of satellite technology. With all of that being said, Skywave OTH radar comes with serious drawbacks, the most prominent being that the system is, as you might imagine given the logistics involved, still incredibly imprecise and difficult to use, even if it is technically more precise than the ground wave alternative. There is even speculation that the Duga radars barely worked, if even worked at all. The Duga radio receiver was 700 meters in width, not because Soviet Russia enjoyed enormous metal structures, but because a receiver of this size was necessary. Now, it's not easy finding concrete information on the dismantled transmitter, but given that radar resolution depends entirely on the width of the beam, assumptions are that the transmitter must have been just as enormous as the receiver. For perspective, a radar beam with a 1 degree width, assuming the target is 120 kilometers away, will receive a signal showing back a 2 kilometer wide target area. This is all good and well, but we're attempting to detect targets thousands of kilometers away using a messy refraction process. Based on the physics involved and using other more modern OTH radars as reference, the Duga radars potentially had an accuracy of around 2 to 4 kilometers, keeping in mind here that most modern commercial GPS has an accuracy of 1 meter. Even still, since Soviet Russia wasn't trying to detect missile launches to the meter, but was rather attempting to detect them at all, the radar system still would have had enormously important potential. Furthermore, Skywave radar is, essentially, due to the angles required, not only limited to around 2 to 4 degrees off of the horizon, but also only works well if the ground along the path of the beam is very reflective. Modern OTH radars have wire mesh extending some 3 kilometers out from the arrays, and there are some hints that this may have been, or was perhaps going to be done, at the Duga radars. Many rolls of wire mesh are still present at the Duga 1 receiver today, and there's the possibility they once served this purpose as well as being part of the receiver itself. And this brings us to one of the more interesting aspects of the Duga radar system. The fact that the refracted signal gathered by the Duga receivers, the part of the signal that was actually informative and could be used to detect missile launches, was essentially nothing more than a barely perceptible drop in a cacophony of deafening noise. In order for operators to actually harvest usable information, extremely powerful low-noise amplification technology advancements, along with then cutting-edge computers, were necessary. The process would have required specialist operators to constantly tune and adjust the frequencies, with a separate group using an additional transmitter aimed directly at the ionosphere to gauge atmospheric fluctuations. This all must have been extremely challenging given the available technology at the time, especially since it's often suggested that Soviet scientists didn't understand the ionosphere at all during the radar's construction. Plus, all of this was made significantly more difficult given the previously mentioned Russian Woodpecker hunting club, plus the fact that it's all but guaranteed that the US military would have been attempting to jam the signal themselves. The Duga radar was, reportedly, very susceptible to jamming, and in conjunction with all the challenges mentioned, it really does raise questions as to just how effective the system was. Either way, whether the radars did or didn't work well, it's generally accepted that the system fell out of use in the late 80s. Woodpecker radio interference declined throughout the 1980s, though partially due to Duga 1 being abandoned after the disaster until ceasing entirely in 1989. The most obvious reason for the second Duga radar being taken offline is the success which saw 7 Russian satellites launch between 1975 and 1979. Each of the 2,400 kilogram satellites were fitted with 50-centimeter infrared telescopes, each specifically tuned to detect the heat produced by missile exhaust systems. Today, the most famous of the radar receivers, Duga 1, is the only large-scale clue of the 2 arrays left standing. The receiver has been left to gradually degrade and decompose in the Chernobyl exclusion zone, serving as a relic of the Cold War era, and more recently acting as a hotspot for adventure tourists, including me. I've been to see it. The receiver has also become something of a media celebrity in recent years, mentioned constantly in TV series, movies, video games, and in various ongoing conspiracy theories.